paper 1. The code is normally 233/1. Then we have another paper, 233/2, that is chemistry paper 2. And there is a 233/3, chemistry paper 3. The first paper, paper 1 and paper 2, each have 80 marks and each have their format. I'll just mention a brief about the two. Paper 1 normally has between 27 and 31 questions. Each question carrying between 1 mark and 3 marks, but each marking point being either half a mark or 1 mark. That is, it is very rare to have a marking point where you write a point and you're given 2 marks for 1 tick. So each marking point is either half a mark or 1 mark. That is in paper 1. And it covers the entire syllabus. We have paper 2 that normally has normally been having 7 questions, but there is a year in 2018 that it was set with 6 questions. So 6 or 7 questions, and each question between 10 and 14 marks. Again, it covers the entire syllabus, but each question is normally targeted to or weighted on specific topics. That is paper 2. Now, having the 7 questions or 6 questions between 10 and 14 marks each question has subsections, A, B, C, or Roman 1, Roman 2. And again, the marking is such that each marking point is either 1 mark or half a mark. So it's important we know that in the theory papers, whatever point we give should either earn you 1 mark or should earn you half a mark, but never 2 marks or 3 marks for just 1 point. Now, we have the practical that has 3 questions normally, or 2 questions. But before I go to the practical, it's maybe good to know how the 3 papers contribute to your overall grade in the national exam. Paper 1 and paper 2, when you total the 2, they total 160 marks. They are the theory paper marks. They are converted to 60%. That is for your aggregate. Or in short, if you get 80/80 in 1 paper, that is 30% in your overall chemistry mark. That is paper 1 and paper 2. When we go to paper 3, which is out of 40, contributes to 40% of your chemistry overall mark. Meaning if you have 1 mark in the practical, you already have 1%. If you have 10 marks, you already have 10% in the practical. So it's very important you take keen interest and attention to how to tackle the practical in a smart way and how to score marks in the practical. Now we get to the practical paper. It's normally made of 2 major parts. The first part, quantitative analysis. And the second part, qualitative analysis. Quantitative analysis, and the second part, qualitative analysis. Quantitative analysis simply tests on your ability. It's about quantities or measurements. So your ability to handle apparatus, perform measurements of volume, temperature, and time, record those measurements or those values that you have obtained of volume, temperature, and time, record them in tables, and then use the data in the tables appropriately. The data that you get can be used for calculations or for representation in graphs. So in a nutshell, it simply tests you about the following skills: performing simple experiments as per the procedure given, performing simple experiments as per the procedure given, recording of values in the tables, recording values in the tables, applying the values in calculations, applying the values in calculations, drawing of graphs, obtaining values from graphs, and using them in calculations, obtaining values from graphs and using them in calculations, and also importantly, interpreting of the graphs or interpretation of the graphs. Now the areas under quantitative, so we've said 2 areas. One, quantitative analysis. And number 2, qualitative analysis. So the areas under quantitative analysis that we'll be looking at that have previously been tested include the following. So we are on the quantitative analysis. Number 1, titrations. Titrations are also called volumetric analysis. Number 2, enthalpy. Also, we call it thermochemistry. Number 3, solubility and solubility curves. Solubility and solubility curves. Number 4, reaction rates. Number 4, reaction rates. And number 5, change of state. That is a cooling or freezing curves. Cooling curves. Just to repeat for those who have joined, that we are saying the chemistry practical or paper 3 is mainly made of 2 parts or 2 areas that are examined. First area, quantitative analysis, which is mainly about measurements, performing experiments where we do measurements of temperature, volume, and time, record those measurements in tables, use the values in tables for calculations, or use the values in tables for graphs. Then we have also said from the graphs, you also obtain other values that you may use in calculations, and you can also be asked to give an interpretation of a given graph. Then we have gone through the areas, major areas under quantitative analysis, where we've said the first one is titration, second one is enthalpy, third one, solubility and solubility curves, fourth area, reaction rates, and the fifth area, cooling curves or curves involving change of state. Now we look at titration. Titration still under quantitative analysis. Now titration, in the last 22 years, titrations have been examined 16 years out of the 22 years. So you can know in terms of probability how it may be probable to always meet a titration question in a practical. There are 3 types of titration. We have direct titration, we have back titration, and we have redox titration. Direct titration, back titration, and redox titration. Each of them has been examined not less than 5 times, as I've said, in the last 22 years. So again, it is important that we remember the basics about the titrations. For direct titration, it is simply either an acid and an alkali, an acid and a carbonate, an acid and a given salt. For example, sodium tetraborate, basic salts. And direct titration makes use of indicators. Makes use of indicators. So examples that have previously been tested include hydrochloric acid and sodium carbonate, hydrochloric acid and sodium hydroxide, sulfuric 6 acid and sodium carbonate. Those are previous examples that have been examined: citric acid and sodium hydroxide, sodium tetraborate and hydrochloric acid, sodium hydroxide and ethanoic acid. So those are examples, not exhaustive, just to give you an idea of what is or has previously been examined. Now, back titrations. Back titrations. These ones involve normally three substances. Two can be a reagent, two can be reagents, and one can be a solid. Three substances, whereby two can be reagents and one a solid, or the three even solutions or reagents. So the basic about back titration, we normally have a pure substance which has a high concentration, pure substance which has a high concentration, being reacted with another substance. But because of its high concentration, that first substance is not completely used up. Some of it remains unreacted. Then the mixture now, which has now the unreacted, maybe we call it substance or solution A, is now performed another titration with the third solution to determine the moles that have remained after the first reaction. Now, the first reaction was involving determining or getting information about one of the reactants that is not known. Could be molar mass, could be percentage purity, and that information now can be obtained by subtracting. Normally there is the subtraction of moles. Candidates are required to always, in back titration, there is some language that you always must have at the back of your mind. The original moles before the reaction, the moles that remained after the reaction, whereby you are supposed to perform a subtraction operation. Now the third, that is redox titration, simply involves using oxidizing or reducing agents. Using oxidizing or reducing agents, and it is characterized by various color changes. So the advantage of redox titration candidates is that normally candidates are provided with the equation. Some of the equations are very complex. Reactions have very complex equations not covered our syllabus. So you are not required to know the equation for the reaction under redox titration, but you are provided with the ratio of moles under redox titration. As I've told you, in the last 22 years, titrations have been examined 16 times, 16 years. So very weighty in terms of if you need to prepare for your exam, ensure you have exposed yourself to titration. The second area is enthalpy. Also called thermochemistry. There are various areas that have been previously examined on thermochemistry. First one, enthalpy of neutralization. Second one, enthalpy of displacement. Third one, enthalpy of solution. The fourth area, thermometric titration. Fifth area, enthalpy of reaction. Enthalpy of reaction. So the fifth area is very wide and general. For any other reaction that we have not or we do not cover in the Form 4 syllabus as an enthalpy that is not covered under enthalpy to be determined. You know, the Form 4 syllabus or what is in your KICD syllabus only mentions enthalpies to be determined experimentally in the lab. That is enthalpy of neutralization, enthalpy of combustion, enthalpy of displacement, enthalpy of solution. Now, this enthalpy of reaction are now enthalpies beyond those. Beyond those. For instance, in 1997, the enthalpy of reaction between magnesium and sulfuric acid. In 2018, magnesium and hydrochloric acid, the practical tested on determining the enthalpy for that reaction. In 2014, the enthalpy for precipitation reaction between copper 2 sulfate and sodium hydroxide was tested. So enthalpy of reaction is wide. Third area that is tested solubility. Third area, solubility and solubility curves. So from my analysis of the last 22 years, this has been examined twice. That is 2006 and 2015. Number 4, reaction rates. Reaction rates. And normally, what has been examined here is the effect of concentration on reaction rates. Normally, effect of concentration on reaction rates. So in the duration which I'm giving you my little analysis, that is 22 years, reaction rates has been examined 4 times. Sorry, not 4, 5 times because of 2019. And number 5, cooling curve. Has been examined once in 2005. Now we want to go back to titration and what it involves. Titration, what it involves and what is expected. Then the other 4 areas, we'll also look at them generally. We'll begin with the titration and then we'll look at the other 4 areas generalized for all of them. So we begin with the titration. Now, when you have a titration question, the question normally begins with, you are provided with. You are provided with. That information at the beginning of the titration question is very vital because you will use it in calculations. Always ensure, if possible, you highlight or take note or underline those values that are given. Is it concentration in moles per liter, concentration in grams per liter, the exact mass provided? You are supposed to highlight and take note of that because it will be used in calculations, those values. Follow the procedure carefully. Follow the procedure carefully before performing the titration. During the exam, you are provided with solutions from the exam council and they may be exact. So before using the solutions with your apparatus, we advise candidates, test your apparatus using distilled water or just water in case they have problems, to avoid spilling your solution, because it's normally the solutions are from the exam council. Be keen on what you have added to which apparatus. If it is a solution that you have pipetted, be keen that you have underlined that solution that you have pipetted and the volume. Check on whatever you are to add to the burette so that you do not make a mistake. And very importantly, where indicators are to be used, be keen not to forget to use the indicator. Because again, you will end up performing a titration that will not have an end point. So that said, after you perform the titration, you will meet the titration table. So the titration table, which I'm sketching, that has 3 titrations normally. The first row, final, burette, reading. Second row, initial, burette, reading. And the third row, the volume of a solution used. Maybe we can call it solution A used in cubic centimeters. The table is normally, after the table, what follows is the first question: calculate the average volume. Calculate the average volume of A, of solution A, solution B, whatever letter of solution, letter assigned to the solution used, you'll be told to calculate the average volume. Now it's important we know how to work smart and always score in this titration table. The table normally has a total of 5 marks, 4 below the table and 1 for the average volume. Total of 5 marks, always. And this is how the marks are awarded, which I want you to be keen to always make sure you score at least 3 marks. At least 3 marks. I want you to look at this scenario. A candidate who has not done even the titration and fills the table, finds a table and fills it as follows. So we have at the first column for the first titration, 19.2. Second one, 19.1. And the third one, 19.0. And because there is an average being asked, the candidate goes ahead. Let me show the average here. Goes ahead to do the average, assuming it is you or me. We perform the average. (19.16 cubic centimeters). Now, this is somebody who has just filled a table and filled it smartly. If you submit such a table to the exam council, you automatically have 3 marks. Whether or not you have done the practical, whether or not the expected value was 30 or 36.5, you will already be having 3 marks. This is how the marks are awarded. The first mark is for completing the table. 1 mark. Completing the table, 1 mark. What will make you to be denied that mark? You will be denied that mark in totality, normally denied half a mark, if your table is not complete. So in complete table, we remove or we penalize half a mark. If your table is inverted, again, a penalty of half a mark. Inverted means the second row for the initial reading being greater than the first row of the final reading. If any of your values, maybe you have interchanged the 0 to be at the top, then it's treated as an inverted table and penalized half a mark. The third penalty is unrealistic values. Your burette goes up to 50 cubic centimeters. So we do not accept, or the council does not accept, any reading above 50. You cannot record 67 or 70 or 51. Any reading above 50 is unrealistic, or any reading less than 1, or any reading that is negative is unrealistic. Number 4, you will be denied the mark if you have a wrong arithmetic. Wrong arithmetic. That is, you have subtracted wrongly. You'll be denied half a mark. You can also be denied half a mark if you add an additional row or an additional column. So do not add any row or any column to a table that has already been provided to you. Don't say you want to do the 4th time and you record number 4 or number 5. Do not add additional rows or additional columns. So complete table 1 mark. And the good news is we do not award a 0 at complete table unless it is blank. So for all those mistakes, whether they are 5 or 6 or 4 mistakes which I've listed, the maximum penalty is half a mark for complete table. So you can only get a 0 if the table is blank, or number 2, if the table does not have numerical values. We've seen candidates fill letters of the alphabet in the table. So those can make you get a 0 at completing the table. The second marking point is on decimal place. Decimal place is normally 1 mark. So you can either score 1 or 0. Again, with the decimal place, the council is looking at to which accuracy have you read the apparatus for measurement that you are provided. Is the candidate aware that when you are given a burette, its calibrations are 0.1 cubic centimeters? So we are interested in the readings, and therefore we only consider the first 2 rows where there are readings. Remember, the 3rd row is not a reading. It is a calculation or a subtraction. But the first 2 rows are actually what you read from the burette. Those readings from a burette should be consistently to 1 decimal place, the 6 of them. So you notice there are 6, uniformly to 1 decimal place, or uniformly to 2 decimal places. The first 2 rows only. If you use 2 decimal places, the second value or the second digit of the decimal must be a 0 or a 5. If you do not comply with any of those 2 conditions, then you score 0 or you are awarded 0 for decimal place or use of decimals. we overlook or ignore use of decimals for a 0 reading at the initial burette reading. So if you write just 0 or 0.00 or 0.0, that one we overlook if the reading is just 0 for the second row only. Third marking point is called accuracy. 1 mark. Normally, when a titration or any practical is set by the exam council, the teacher in charge of chemistry in a given school performs the experiment and sends his or her values to the exam council. Upon receiving those values, the exam council now uses the teacher's value as the school value, the teacher's average value as the school value, which we write on top of the table. We can write school value, for instance, is equals to 19.3. I'm just giving an example. School value equals 19.3. Now, for you to score on accuracy, we look at any of the 3 titrations that you have done or that are recorded there. If there is any of them whose volume gives plus or minus 0.1 of the school value, then we tick it and we award 1 mark for accuracy. This is simply a measure of whether the candidate did the practical to precision, just like his or her teacher. Now, if there is no value that is within plus or minus 0.1 of the teacher's value, we go ahead to look for plus or minus 0.2. And if it is there, we now award half a mark. But if a candidate had scored the 1 mark for plus or minus 0.1, then that is the maximum. We don't award a second time. If there is none that is within that range, then you score accuracy 0. Now, take note that supposing a candidate had done an arithmetic error in subtraction, the examiner normally performs the subtraction as it was supposed to be done and writes the expected answer or expected value of volume beneath the candidate's value. So supposing, like in my case, one of the titrations, a candidate had written 19.3 or 19.6 instead of 19.2, for instance, the first one, the examiner will do the subtraction correctly and write 19.2 as required or as expected. Now, when it comes to accuracy, the mark for accuracy will be awarded based on that correct subtraction. Based on the correct subtraction and not the values that you had given, when supposing they were wrong in terms of subtraction. The 4th marking point is on principles of averaging. Principles of averaging, 1 mark. You are supposed to average only values that are to a maximum of plus or minus 0.2 of each other. So I want to give an example of different sets of values. So different sets of values. For instance, 20.2, 20.4, and 20.6. That is a first set. Another set, 34.4, second set. That is set 1, set 2, a third set, and a fourth set, so those are values. I hope we understand. May separate them with commas to indicate that they are different values. Now we look at set 1. Set 1, 20.2, 20.4, and 20.6. Normally, you would imagine that the average should be the 3, 20.2 plus 20.4 plus 20.6 divided by 3. But if you perform that averaging, you will score 0. You will not score a mark. The reason is because out of the 3, there are 2 values, 20.2 and 20.6, whose difference is exceeding 0.2. And therefore, you cannot average the 3. You are supposed to choose 2 and average them, that is add 2 and divide by 2. So you can choose 20.2 plus 20.4 divide by 2. You get 20.3. Or 20.4 plus 20.6 divided by 2, you get 20.5. Do not do 2 averages. Choose 1 and stick by it. Do not do average of averages. That is, you do both averages, then you go ahead and do another average. Again, you will not score on averaging. We look at the second set of values, 34.4, 34.5, and 35.0. Now there, we only have 2 values that are consistent. In titration, consistent or consistency is simply values that are a maximum of 0.2 plus or minus 0.2 from each other. So we only have 2 values that are consistent there. That is 34.4 and 34.5. When we look at 35.0, it is not consistent with any value there, and therefore we omit it in the averaging. We say 34.4 plus 34.5 divided by 2, which is 34.45. Third case, we are supposed to average the 3 values. And one area that candidates fail is making assumptions. Just because you have gotten 23.0, 23.0 and 23.0, you fail to show the working. The working must be shown, even if it appears the answer is so obvious. 23.3 plus 23.3 plus 23.3 divide by 3. Supposing you decide to do only 2 of them and divide by 2, again you will miss on averaging. You should not omit a value to be averaged if it qualifies to be averaged. That is, if it is consistent with the other values. The fourth set of values, 30.4, 31.2, 28.0. None of those values is consistent with each other or with another, and therefore there cannot be an average from such values. What does a candidate need to do? Supposing you get those values, you are supposed to perform the titration a 4th time with a lot of keenness. Chances are that either the solutions that you are using, you had not made them homogeneous by shaking them, or you are not concentrating while performing the titration. Your attention was elsewhere. So you end up overrunning the solution from the burette to the pipette, even past the end point. That is what leads to such values. So you are supposed to perform the titration a 4th time, but don't add a 4th column, as I said. Perform a 4th time with a lot of precision, adding small portions. And you will notice that time, at least you can get a value that is consistent with any of the 3. Then you edit your table by filling in now values, at least 2 values that are consistent. Now, notes under principles of averaging. We have said you must show you are working. The marks are awarded half-half. First step for showing either 2 values divide by 2 or 3 values divide by 3, that is half a mark. Second, half a mark is at the answer. The intermediate step may or may not be shown, but it does not earn a mark. Whereby, for instance, here, we could have said 57.2 in my example, 57.2 over 3. You may or may not show, but it does not earn a mark. The answer must be to 2 decimal places where you are rounding it off. Where the answer is being rounded off, it must be to 2 decimal places. Never leave your answer, never round your answer to less than 2 decimal places. However, if the answer works out to exactly a whole number or 1 decimal place without rounding off, then that is acceptable. If the answer works out to 1 decimal or less, that is a whole number, exactly without round off, then the answer can be accepted in either whole number or 1 decimal place. We allow truncation or rounding off. You can truncate or round off. Like in my case, I truncated. You will still score. Units may or may not be shown. They are not compulsory for you to earn the mark of averaging. You may or may not show units. But if you show them, they must be correct. Because we normally see candidates making the mistake of writing centimeter squared, which is not a volume, is area. So that is under averaging. And the last mark is called final accuracy. 1 mark. For a candidate to score on final accuracy, again, we look at the teacher's value and compare with the candidate's average, calculated average for the candidate. If the values are within plus or minus 0.1, then you score 1 mark. The candidate scores 1 mark. If the values are not within plus or minus 0.1, but they are within plus or minus 0.20 of the teacher's value, teacher's average titer, then we award half a mark. Otherwise, you score final accuracy 0. So the total marks for the table are 5 marks. 5 marks. And as I told you, any candidate who gets to an exam room and fills a table, just like I filled, even without performing the titration, should score 3 marks. The marks are completing the table, decimal place or use of decimals, and principles of averaging. The other 2 are dependent on the teacher. So you always should strive to score 3 marks in any titration table. That is 3 out of 40 in a practical exam, and already 3% in your overall chemistry exam whenever you see a practical, a titration table, sorry. Now, what follows the table? What follows the table are calculations. What follows the table are calculations. The calculations should be entirely based on or dependent on the value which you gave at the titration table. And it's important to note that at this area, there is no fixed answer. As many as the number of candidates as there are in the Republic, all their answers are correct in the next step or next steps, so long as you apply them correctly. I want to give a case, an instance, or a sample of a calculation. You could be asked, calculate the number of moles of solution A, which is sodium carbonate, that were used. Calculate the number of moles of solution A, sodium carbonate, that were used. And at the stem or at the beginning of the question, you had been told you are provided with 0.15 m or molar sodium carbonate. Now at this point, the marking scheme simply tells us to mark as follows: number of moles, I'm just giving the case of 0.15 m, number of moles of solution A, they are equals to 0.15 times the answer in part A over 1000. So it does not matter whether you had failed under principles of averaging. It does not matter even if you had given unrealistic values as your answer at part A. Even if you had given a value of 12 million or 9,000, If at this point, if that was the average titer that you gave, and of course you are failed under principles of averaging, if at this point you come and you substitute 0.15 times the 12 million over 1,000, you will score 1 mark. If you go ahead to use your calculator and get the expected calculation, the expected answer to that calculation, again, you score another marking point. The next question could be calculate the number of moles of hydrochloric acid that were used. Again, the exam council gives the directive mark as follows: number of moles of HCl equals the answer in B. Maybe this is now part B. Let me check on this part B. Answer in B times 2, because the mole ratio probably is 1:2. Answer in B times 2. So supposing you had your 12 million as your answer in the average titer and you've moved ahead, then at this point, whatever you had calculated previously and gotten an answer, if you go ahead and multiply by 2, whatever you had above there, you score the full mark. And it goes on and can even total up to 14 marks, just being awarded for simple transfer of values. Simply transferring of the values up to the very end. Now, supposing in this part B, the candidate had gotten a wrong at this point of the answer. Maybe had written a wrong answer. Here he or she had gotten correct, but at the answer gotten wrong. If the candidate proceeds in Roman 2 or part D, whichever now we say the next step, and applies that wrong answer, multiplies it by 2, if it is required to be multiplied by 2, the candidate scores the marks fully. So wherever you fail, if you go to the next step and still use the value that you failed with in the calculation as required, you will score fully for those marks or for that step. And it goes on and on. The only penalty comes in at the very final step or the final question, the final answer, where we are advised or instructed to penalize only half a mark if the very final answer exceeds a certain range. So in a question of 14 marks of a titration, a candidate can readily score from the table 3 marks or loses 2 marks because of the accuracy mark or the teacher's value. And at the calculation, all the marks except the half a mark. So out of 14 marks, a candidate can score 11.5 in any titration question, even without having performed the titration, by simple transfer of values. At this point, before I wind on the titration, I want to mention about rounding off of values. And I'll simply sum it up by calling it the 234 rule. 234 rule, which is talking about decimal places. 234 rule or 234 rule. 2 decimal places. All volumes must be given or rounded to 2 decimal places. All volumes must be rounded to 2 decimal places. And that includes even the theory papers. The 3 stands for 3 decimal places. All molarity or concentration in moles per liter must be rounded to minimum 3 decimal places. All molarity must be rounded to 3 decimal places, or all concentration in moles per liter. 4 decimal places. All number of moles. All number of moles must be rounded to minimum 4 decimal places. All number of moles must be rounded to minimum 4 decimal places for you to score. Otherwise, the penalty for rounding off is normally penalizing on the answer. The answer is penalized if you do not round to those decimal places as shown or as mentioned, as I've advised. Now that is all about titration. We go to the other areas. That is still on quantitative analysis. We mentioned other areas: thermochemistry, solubility, reaction rates, cooling curve, thermochemistry, solubility, reaction rate, and cooling curve. Now, all those areas normally have tables, different tables. I'll only draw a sample of one to represent the others, a sketch of one. So temperature, degrees Celsius. I hope it's legible. Time in seconds: 0, 30, 60, 90, 120, 150, 180, 210, 240, and 270. So I'll just call that table A. Another one, table B, on rates. Then we have beaker 1, and beaker 2. Maybe this is a solution A, solution B, solution C, solution D, and then distilled water. Then solution E, then time, and 1 over time. Time in seconds and 1 over time. Now, the first table is common for questions on enthalpy, questions on solubility, questions on cooling curve, and has been examined quite a number of times. The second table is a sample of a table for reaction rates. Now, all these tables and many other are awarded in the same, awarded marks in the same format. So the first marking point for all these tables is completing the table. And here, depending on the size of the table or the calculations in the table, completing the table ranges between 2 and 5 marks. Can be between 2 and 5 marks. The second marking point is on decimal place or use of decimals. Normally, 1 mark. Decimal place, 1 mark. The third mark is on accuracy, 1 mark. And the fourth marking point is on trend, 1 mark. So the table can range between 5 marks and 8 marks. Table can range between 5 marks and 8 marks. Now, I'll just quickly go through the marks for, or what we look at each marking point. What is it we look for you to score the mark? Completing the table. You will miss the mark for completing the table if your table is incomplete. That is, for every blank space, you are penalized either half a mark. The minimum mark you can score in completing the table is half a mark if you had filled the table. That is the lowest mark. You will miss the mark if you have unrealistic values. For every experiment or every practical, there are expected realistic values. Take, for instance, you are measuring the initial temperature of a solution which you have not reacted anything with it. So that temperature should always be less than 40 and greater than 10. I'm talking of a solution which you've not done anything to it, not reacted anything. You found it in the lab. The initial temperature should not exceed 40 and should not be less than 10. That is just an example. We are talking of, for instance, rate of reaction. We are expecting time for the first experiment to be less than 1 minute, and yet you get maybe 400 seconds for the first experiment. Those are unrealistic values that will make you to lose the mark for completing the table. Where a table, we expect changes in values, all these tables we expect changes in values as the experiment progresses. So where a candidate feels constant values, constant readings all through, you are penalized for the complete table. Actually, you are penalized almost all the marks and only awarded half a mark if you fill constant readings all through the entire table where they are not required constant. You will be penalized again almost all the marks for complete table to only be left with half a mark if you add an additional row or you have two sets of readings or values in your table. That is penalized almost the entire marks for completing the table. The next marking point is on decimal place. And here I'll just emphasize on the following. All these other areas are using the stopwatch or the thermometer. I begin with the thermometer. Thermometer readings must either be whole numbers consistently used or one decimal consistently used. Thermometer readings must be whole numbers consistently used or decimals, one decimal place consistently used. If one decimal place is consistently used, the value of the decimal should be 0.0 or 0.5 only. Otherwise, you miss the mark of decimal. It is either you score 1 mark or 0 marks if the decimals are not consistent. So whenever you do a practical, it's important you confirm your recordings for readings, whether the decimals are consistent. Stopwatch readings must be either consistently recorded as whole numbers or consistently recorded as one decimal place or consistently recorded as 2 decimal places. Secondly, stopwatch readings must strictly be in seconds only. So where your stopwatch has exceeded to minutes, convert the minutes to seconds. Accuracy. Again, the exam council uses the teacher's value. The teacher also does this experiment and forwards his or her results to the exam council. The exam council uses the teacher's values or value, more so for just one reading. Most commonly for the enthalpy questions, the exam council may mention the temperature which the teacher recorded for the first experiment is what is used as the school value, and the one where the candidates' values are compared with. The same for the reaction rates, could be for the first experiment. Now, for a candidate to score on accuracy, his or her values must be within plus or minus 2 degrees Celsius of the teacher's value for temperature readings that are being compared, plus or minus 2 degrees Celsius of the teacher's readings for temperatures that are being compared. or plus or minus 2 seconds for time readings for the experiment which a comparison is being made. Plus or minus 2 seconds for time reading, where time is the one being compared. Otherwise, you score accuracy, no mark, if the compared reading is not within that range. And the last mark is called the trend. The trend. In any given table of such experiments, there is the expected trend. Some of the trends, especially for enthalpy, can include a continuous rise, then constant, then drop. Or a constant readings, then a rise, then a drop. Or continuous drop, then constant, then rise. So there are various trends that we look at in the table. They are unique for any given question that has been examined in a particular year. For rate, the trend is normally time must be increasing, especially where you are adding distilled water in subsequent experiments. The time should be increasing. So that is the trend that is marked. So those are the marking points for the tables. Tables that are under enthalpy, solubility, cooling curve, and reaction rates, marked in the same way. Now, all those tables are normally followed by graphs. All those areas that I've mentioned have been normally followed by plot a graph. Remember, the essence of this session is to make sure you work smartly and ensure you score marks. At least 15 marks or 16 marks out of 40 can make you not score a D grade in chemistry in this practical exam. So we are just looking for those few marks on how to work smart and not score any D grade in chemistry. So other free marks are found in the graphs, and graphs are marked as follows. If you are asked to plot a graph of temperature against time, temperature against time, there are 4 marking points under graphs. First marking point, labeling of axis. So whenever you see any graph that is to be drawn, that you are told to plot a graph, first thing, draw the axis and label them. Of course, you make them axis by having the arrows at their tips. Draw the axis and label them. You have half a mark. The next marking point is on the scale. Half a mark. The scale is simply how have you used the graph space. in terms of the distance from the lowest plot to the highest plot. How much of the graph space has it used? You are supposed to use over half of the graph space between your lowest and highest plot horizontally should occupy over half of the graph space. Between your lowest and highest plot vertically should occupy also over half of the grid or the graph space provided. Do not state the scale. We don't need a statement of the scale, and if it is there, it will be ignored. So do not write 1 centimeter represents 2 boxes. Simply utilize the space and you will score on the scale. Third marking point is plots, which carries a full mark. Plots is simply testing whether you are able to transfer points on the table to the Cartesian plane which you have drawn, calling a graph. Are you able to locate a given coordinate in your space that you are provided there? Supposing it's at 0 time and a temperature of 23, are you able to locate temperature or coordinate 0, 23 on the graph? And the fourth marking point is on the line or shape of the graph, and that carries 1 mark. I want to revisit on the scale. On the scale, graphs of solubility, cooling curve, and enthalpy need not have an origin of 0, 0. You can have an origin of 0, 21, where 0 is placed there to show that it is applying for the horizontal axis, and 21 is placed at that point to show that it is applying on the vertical axis or the y-axis. Do not place the 0 there. That is marked wrong. Don't place the 0 there because it would mean it has been applied both to the x and the y-axis. So if you put a 0 there, it means this interval is of 22 and the next interval is 1. That is unequal intervals, and that will lead to scale scoring 0 and plot scoring 0. So those are the 4 marking points on graphs. Whenever you see any graph, try to score at least 2 out of the 3 marks. That is labeling of axis, scale, and the plot. The line, if you have no idea, you may not score it as expected. What follows graphs are questions of from the graph determine. From the graph determine. For you to score in such kind of a question, you must show where you are getting the reading from the graph. Where you're getting the reading from the graph. You must show using a broken line from the horizontal axis and the vertical axis to that point that you're making the reading. on the graph. That is, you must show where you have obtained your value from. Now, the punitive part about graphs is that if you did not score, or if a candidate does not score and align the last marking point under the graph, and it is a graph of enthalpy or a graph of solubility or a graph of a cooling curve, then marking is not awarded, or marking does not award that point where you have made a reading. That is, the exam council insists on readings from a correctly plotted graph or a graph whose marking point of line was awarded fully. So that is normally punitive. However, any other question that follows, whereby you have now you had given a reading that was failed, but any other question that follows that may be requiring a calculation, if you use that reading, you will score fully. I want to give a case whereby, for instance, we have this graph for getting delta T, and probably the candidate did not follow the rules well when it comes to plotting the graph. For instance, one of the rules of the line is that the line of best of fit must pass through the first plot. So you may draw a line of best of fit and omit the first plot. That way, you find you will miss out on line, and any reading from the graph will not be awarded. However, where now a calculation is required, and you are required now to apply a delta T, if you apply whatever reading you had written, even if you had written 5,000, again you will score fully. Supposing you had written delta T is 2020. And then where now a calculation is required, you apply it. Delta H is MC delta T, and somewhere you multiply your 2020. Then you will score fully. We do not deny marks or penalize twice. Calculations on delta H. Delta H equals MC delta T. The equation should be shown, though it does not score. The equation should be shown, though it does not score. Where there is kilojoules, the K must be written as a small letter and the J as a capital letter. Where you are calculating enthalpy, the sign must be shown. Where you're calculating enthalpy, the sign must be shown even when it is positive. The sign must be shown even when it is positive. Now, the other graph is on reaction rates. Graphs on reaction rates. Now, these all graphs of reaction rates that have 1/T plotted against either volume or concentration are straight line graphs that pass through the origin. Whenever you are dealing with a graph of reaction rate, 1/T, it must be a line of best of fit, straight line passing through the origin and two other plots and 2 other plots. So graphs of 1 over T versus volume, or 1 over T versus concentration, are straight line graphs, lines of best of fit that must pass through the origin. Now at this point, I want to summarize on that first part by urging all the audience, students, kindly make sure that you maximize on the free marks in the practical, especially on that first part of quantitative and qualitative, quantitative analysis, First part of quantitative analysis. Why do I say capitalize and score those free marks? That part of the practical is the only part where we do not have an expected answer. And since the examiner is not there to prove whether or not you did, you can easily even fill values and work smart and score fully in those areas, and even plot a graph and score from the graph. I'm not encouraging you not to perform the practical. Perform the practical because you need the accuracy mark, and you also need the final mark, which you are told, the final value, which you are told must be within a given range. You need it to be within a given range. But I'm just encouraging you, if you work smart, in the first part of the practical, you can easily even score up to 15 marks on that part alone. And that part does not have values provided by the exam council. Your answer is correct. Still on the same note, I discourage candidates from the tendency of collusion or trying to look at what the other candidate has obtained, because it does not help. You risk scoring grade Y for collusion, and probably you could be the one who is correct, yet you are busy looking at your friend's value, which is wrong. All the values are marked according to how you have applied them, and you are awarded fully if you apply them well. So never bother to know what your colleague has obtained, whether during or after the practical, because the values are not fixed values. The values are the candidate's values that we mark and we award accordingly. At that point, I want us to pause and invite questions before we get to the second part, that is qualitative analysis. Normally ask questions at the end. I'm halfway now. At the end. Oh. Even this part, just the presentation will go up to 5. I told Madam it's normally 3 hours. Yeah. I'm advised we will have questions at the end of the session. So we proceed with the second area, that is qualitative analysis. Qualitative analysis. Now, this area of the practical is simply delving into that definition of chemistry where in Form 1 you mentioned the study in part of the definition of chemistry. What is chemistry? You said study of the composition, properties of matter and the changes that matter undergoes. So this part deals with the composition of matter, where you are provided with substances and we are supposed to identify or to carry out tests to know what those substances are made up of, composition of those substances. So this qualitative analysis is divided into two areas. We have inorganic qualitative analysis, inorganic qualitative analysis, and organic qualitative analysis. So under inorganic qualitative analysis, normally deals with ionic substances, normally ionic substances or substances which consist of metallic cations, non-metallic anions, while organic qualitative analysis deals with organic substances. We begin with the inorganic qualitative analysis. There are various tests which we will be going through. Various tests which we will be going through under the inorganic qualitative analysis. So I will just be highlighting some of those tests and moving with a little more speed, so you get the points, especially on what is expected, observations, and inferences. So the first test is describing appearance. Describing appearance. If you are told or asked to describe the appearance of a substance, there are two marking points that we look at. Either the substance should be powdery or crystalline. And number two, you must mention its color. So number one, whether it is powdery or crystalline, and two, the color. I've not given in the order in which you will describe. In fact, I've inverted the order. So an example would be, supposing a solid provided P is, for instance, copper 2 carbonate. If you are asked to describe its appearance, you would simply say it is a green powder. If you are asked to describe the appearance of sodium chloride, maybe it is not known as sodium chloride, but it is provided as a solid Q. You would mention white crystals. So color and the fineness of division. Is it crystals? Is it powder? You may use language like white crystalline solid, but the marking point is the white, and the other marking point is the crystals. Number 2, addition of water. Addition of water. And here we look at observations and inferences. I want us to learn a simple mnemonic or acronym to always remember, and we say Kcse. Standing for copper 2, iron 2, and iron 3. Copper 2, iron 2, and iron 3. Now, addition of water. What are the possible observations? The first observation, which is a marking point independent, is whether or not the solid dissolves in water. So that statement earns a mark on its own. Solid dissolves in water. Then you follow with the phrase to form either a colorless solution or a colored solution, a green solution, blue solution, brown solution. So you just say solid dissolves to form a, and leave a dash, solution. The part of now solid dissolves. The inference that goes hand in hand with that is that the solid is soluble in water. Solid is soluble in water. Do not say the solid is polar at this point, because when you say a solid is polar, you are implying it is a molecular substance. So you use the word polar under organic chemistry. And even the question could have started by, you are provided with an organic substance. But under inorganic, we don't use the word polar. We simply say is soluble in water. It earns you a mark at the inference. Then the other phrase of dissolves to form a colorless solution. The inference should be absence of Kcse, which I have told you we are using just for our communication. Absence of Kcse. Do not say absence of colored ions. That is now rejected. You must specify and mention the 3. Absence of copper 2, iron 2, and iron 3. We can also add water to a solid, and the solid does not dissolve. So the other observation, which is now beneath that, could be solid partly dissolves. We do not say does not. Simply say partly dissolves to form a, you leave a dash, suspension. So dash is for the color. Can be to form a white suspension, to form a blue or a green suspension. Remember, you do not say it forms a precipitate. A precipitate is formed from solutions. A suspension is formed when you are adding an insoluble solid to a solvent. So here you use the word suspension. The inference for that would be the solid consists of a soluble and an insoluble substance. Solid consists of an insoluble and a soluble substance. Third test. The third test, heating. Heating. Gently, then strongly, or just heating. Remember, this is not burning, it's not igniting. This is placing a solid in a test tube or boiling tube and heating. So expected observations. You are supposed to note whether the solid gives off a colorless liquid droplets forming on cooler parts of the test tube. That is one expected observation. Colorless liquid droplets forming on cooler parts of the test tube. Never write or do not write colorless liquid condenses. That is penalized because liquids do not condense. It is gases that condense. You are supposed also to test the gases using moist red and blue litmus paper. I'm still on the point of heating. Test gases produced using moist red and blue litmus paper. You are supposed to record the observation on each litmus paper. Mention red litmus changes to blue. Blue litmus remains blue. Do not use the language remains the same. That is rejected as an observation. Don't say red litmus remains the same. You say red litmus remains red, blue litmus remains blue or changes to red. You are also under the observations supposed to mention the residue, color of the residue. Is it a white solid? Is it a black solid? So describe the nature of the residue. Now the inferences that follow depend on the observations. For instance, if you mentioned that a colorless liquid droplets form on the cooler parts of the test tube, the inference would be the solid is hydrated or contains water of crystallization. If you had mentioned blue litmus changes to red, red litmus remains red, the inference would be acidic gas produced. If you had mentioned red litmus changes to blue, blue litmus remains blue, the inference would be ammonium ions, NH4 present, NH4 plus. Number 4, addition of sodium hydroxide dropwise till excess. Addition of sodium hydroxide dropwise till excess. Again, we are going to have acronyms or mnemonics to remember. First one, CAM. Second one, ZAP. CAM standing for calcium ions, magnesium ions. ZAP standing for zinc ions, aluminium ions, and lead-2 ions. And so those 5 cations, CAM and ZAP, summarize for sodium hydroxide. For all the possible observations of sodium hydroxide, if the solution was colorless at a previous test. How do they summarize? I'll just quickly go through. For sodium hydroxide, whenever you add it dropwise till excess, you either expect a white precipitate or no white precipitate. So never say no observable change, never say colorless solution formed. You must start with whether there is a white precipitate or no white precipitate. So no white precipitate, that would mean what? CAM and ZAP absent. You must mention the 5. Calcium, magnesium ions, zinc ions, aluminium ions, and lead-2 ions absent if there is no white precipitate. Second possible observation, white precipitate insoluble in excess. White precipitate insoluble in excess. And here it would be CAM, calcium ions or magnesium ions present. Third possible observation, white precipitate that dissolves in excess or soluble in excess to form a colorless solution. And there you would have ZAP, zinc ions, aluminium ions, lead-2 ions. And of course, sodium hydroxide, there are what we had previously mentioned, Kcse, copper 2, iron 2, and iron 3. So for those, the precipitates would have the respective colors. For copper 2, blue precipitate, iron 2, green precipitate, and iron 3, brown precipitate. However, for iron 2 and iron 3, a test can be conducted whereby, and I'm giving a case of of a particular 2 particular years. In the year 1999, there was one of the tests of adding sodium hydroxide to one sample in a test tube, and a green precipitate was formed. Then the next test in that very year, in another sample now, in a test tube, the candidates were to add 2 drops of hydrogen peroxide to the sample and then repeat the test for sodium hydroxide. And the observation was a brown precipitate. Now, because a candidate had already written, or you had already written ion 2 present in the previous test, and here a brown precipitate has been formed, you cannot say ion 3 present. The expected inference was ion 2 oxidized to ion 3, but not just saying ion 3 present. I said I will give 2 examples. The other example now was the converse of such a test in 2007 Kcse chemistry paper 3. There was addition of sodium hydroxide to a sample, and to that sample a brown precipitate was formed. Then the candidates were supposed now to pick another sample which hasn't been added anything and add potassium iodide, then repeat the test for sodium hydroxide. The second repeated now test gave a green precipitate. And of course, now the inference that was expected was ion 3 reduced to ion 2. That is to say, you cannot perform a test and say ion 2 present, then do other tests in between, then repeat now a similar test, and you come and say ion 3 present. That would be contradiction. You only need to know the transition. Ion 2 gets oxidized to ion 3, and conversely, ion 3 gets reduced to ion 2. Test number 4, ammonia solution. Dropwise till excess. Here, we talk of zinc and another acronym, MAP. MAP. So MAP stands for magnesium, aluminium, and lead 2. So ammonia solution, whenever a solution is colorless and you are adding ammonia solution, you must have those 4 cations in mind. Zinc on its own, then MAP, magnesium, aluminium, and lead 2. So first possible observation for addition of ammonia would be no white precipitate. No white precipitate. You do not record no observable change. Do not record colorless solution formed. Do not record no observation. Should be no white precipitate. Do not also record no precipitate. Again, no precipitate is awarded half of the marks because you are supposed to say you expected it white. So no white precipitate. The inference would be zinc and MAP absent. That is 4 of them, zinc and MAP, magnesium, aluminium, lead 2. Second possible observation would be white precipitate insoluble in excess. And the inference would be MAP, magnesium, aluminium, or lead-2 present. Third possible observation is the confirmatory test for zinc. White precipitate soluble in excess, which the inference would be zinc ions present. Now, those four are the major solutions that are used to eliminatively identify cations. There are other solutions that are used to identify cations. That is sodium sulfate. So I will just now give the name and the cations or the acronyms for the cations. Sodium sulfate or sulfuric 6 acid. All these are solutions. So I was looking for acronyms, and the easiest I got is CALEB. Calcium, lead, and barium. Calcium, lead-2, and barium. So this is calcium ions, lead-2 ions, and barium ions. So sodium sulfate tests for the presence or absence of those three cations. The expected observation is either white precipitate or no white precipitate. To the next one, sodium chloride. Solution. And here the acronym, LESI, or you can say SILE. Lead, 2, and silver. Where again, white precipitate or no white precipitate. Now the next tests are normally for the anions. Barium chloride or barium nitrate can be followed by HCl or just on its own. We need an acronym for this. There is a certain part of our republic where they greet each other like this. That is Sasako. And we can use that as our mnemonic. Sulfate, sulfite, and carbonate. Barium chloride or barium nitrate tests for the presence or absence of those three anions. The expected observation is, of course, either a white precipitate or no white precipitate. Hydrochloric acid or nitric 5 acid can follow barium chloride, and that now distinguishes carbonate and sulfite ions, because if they had formed a white precipitate, the two anions react with acids and the white precipitate will dissolve. So hydrochloric acid or nitric 5 acid can now be used to distinguish between sulfite and carbonate and sulfate. That is after performing the test of barium chloride. Similar to barium chloride is lead 2 nitrate. Lead 2 nitrate. Lead 2 nitrate is normally tested by being followed by warming. Followed by warming. And I may just put it, sometimes acidified lead 2 nitrate followed by warming. Acidified lead 2 nitrate followed by warming. When it is acidified, it only tests for sulfate ions, chloride and bromide. This is an emerging issue from Kcse 2019, that bromide also is tested using lead 2 nitrate and behaves the same as chloride ion. So when acidified and warmed, a white precipitate that remains on warming would imply sulfate ions. White precipitate that remains on warming, the inference would be sulfate ions. But a white precipitate which dissolves on warming, the inference would be chloride or bromide ions. Chloride or bromide ions. A yellow precipitate would imply iodide ions. Test number 9. Test number 9. Devada's tests. For nitrates. This was examined in Kcse 2012. Devada's test for nitrates. What does it entail? It simply involves addition of sodium hydroxide to a solution, followed by aluminum foil, followed by warming. Addition of sodium hydroxide, followed by aluminum foil, followed by warming. The observation would be effervescence producing a gas which changes red litmus paper to blue. effervescence producing a gas which changes red litmus paper to blue. That inference would be nitrate ions present. Test number 10, use of oxidizing agents. Use of oxidizing agents. Acidified potassium manganate 7 or acidified potassium dichromate 6. Use of oxidizing agents, that is acidified potassium manganate 7 or acidified potassium dichromate 6. Now, under inorganic chemistry, these are used to identify sulfite ions. They are used to identify sulfite ions. So we've said acidified, so these are for sulfite ions. Sorry, sulfite, not sulfate. SO 3, 2 negative. Even under the theory papers, you could be asked, how can you distinguish carbonate ions from sulfite ions? Carbonate ions and sulfite ions, how can you distinguish? So you use the oxidizing agents. Sulfite ions will change the oxidizing agents from to their expected colors. Potassium manganate 7 from purple to colorless. Potassium dichromate 6 from orange to green. And lastly, on inorganic chemistry, pH, which may include red or blue litmus papers, using red or blue litmus papers. And under this, we note the following. The anions that are acidic ions, both anions and cations, include acidic cations and anions. So supposing blue litmus changes to red, or pH is less than 7, then you mention that that is an acidic solution. The cations that are acidic are hydrogen ions, hydroxonium ions, aluminium ions, and the anions that are acidic, hydrogen sulfite ions. So all these are acidic. The basic cations are hydroxide, carbonate, and hydrogen carbonate. Those are basic anions. Why do I say so? Because in the previous years, 2016, there was a test where under inorganic chemistry, you are supposed, or they added universal indicator. And one of the inferences was that the solution was weakly basic, and the inference expected was that hydroxide, carbonate, hydrogen carbonate. The same was in 2006, where there was addition of red litmus paper to a solution, and the solution changed to blue. So candidates were expected to write presence of hydroxide, carbonate or hydrogen carbonate. So that winds for inorganic chemistry. We are on the last bit of qualitative analysis, and that is organic chemistry, organic qualitative analysis. I'll quickly go through the tests. They are 10 in number, but I will move fast in the interest of time. First test, addition of water. Addition of water. The expected observation. Solid dissolves or liquid is miscible. Solid dissolves or liquid is miscible. Whose negative is, you can have the negative of that. Solid partly dissolves or liquid is immiscible with water. So either of the two. Of course, when we say dissolves, you say to form a colorless solution, but the marking point is at the dissolving. When you say liquid dissolves or liquid is miscible, you talk of forming a uniform solution. The marking point is liquid dissolves or is miscible. Again, when you say it does not dissolve, you mention what is formed. If it is liquid is immiscible, forms two layers, like we had in 2019, where there was cyclohexane and xylene, if you are following even in the news. Liquid forms layers, is not miscible and forms layers. So again, here the inference here is either the substance is polar or the substance is non-polar. So remember, under inorganic, we said don't use the word polar. You use it now under organic chemistry. You can say solid is polar, or liquid is polar, or liquid is non-polar. Number two, addition of ethanol. Addition of ethanol. So the observations are similar to that of addition of water. However, the inference are the opposite. Observations are similar to those of addition of water. That is to say, you can observe that the solid dissolves to form a colorless solution, or liquid is miscible to form a homogeneous or uniform mixture, or one layer. Or you can say the solid does not dissolve, or the liquid does not dissolve. Now, interestingly, with ethanol, when a substance, a solid, dissolves, then we say it is non-polar. Solid is non-polar. Same for the liquid, non-polar, when it dissolves in the ethanol. Number three, burn or ignite. Burn or ignite. Before we proceed now from number three onwards, it's important we know that from the third tests, the subsequent tests, that is test number 4 onwards, the tests are normally to identify the three main functional groups or homologous series under organic chemistry. First one is the one of double bond. The other one is the one of triple bond. And the other one, ROH. And this other one, RCOOH. Now I said three major, though you notice I've put four, because the first two go hand in hand. You can either mention one or both, and they score each on behalf of the other. That is, you can score, once you mention one, you score the full marks. The other two are independent. So we are on test number 3. Is that so? Burning. Burning. So whenever you are burning, possible observations that are expected: burns with a yellow, sooty, stroke smoky flame. Burning, burns with a yellow, so burning is stroke igniting, yellow, sooty or smoky flame. We also accept the word burns with a luminous, but you must mention sooty or smoky flame. Now here, carbon to carbon double bond or carbon to carbon triple bond present. That is the inference. The other observation would be burns with a non-sooty flame. Burns with a non-sooty flame. Could be blue or even yellow, but we simply say non-sooty flame. Where the inference would be those two are absent. It's important that we note that for you to score on these functional groups, each carbon must be having 4 covalent bonds. Do not attach any atom or radical to the carbons that you are showing the double bond. The angle does not matter so long as each carbon has 4 bonds, such that a structure like this one at the corner here is accepted, so long as the carbon has 4 covalent bonds and they are open. However, we reject if a candidate leaves the answer like that, or if a candidate, so this is marked wrong, or if a candidate leaves the answer as carbon to carbon triple bond like that, again, that is marked wrong. Number 4. Universal indicator and pH. Universal indicator and pH. So here, a candidate is supposed to give one pH value. Whenever you use the pH, give a single pH value. Give a single pH value. Never give a range. Never give a range. And the same applies under inorganic chemistry. The observations and inferences that are accepted between pH 1, 2, and 3, any of those, the inference is strongly acidic. Inference is strongly acidic. pH 4, 5, 6. Weakly acidic. pH 7. pH 7, neutral. pH 8, 9, 10. Weakly basic or weakly alkaline. Weakly basic or weakly alkaline. pH 11, 12, 13, and 14. Strongly basic or strongly alkaline. We reject weak acid or weak base, strong acid or strong base. We reject that. So you give those observations. Test number 5. Addition of sodium carbonate or sodium hydrogen carbonate. Addition of sodium carbonate or sodium hydrogen carbonate. Expected observations and inferences. You either expect to see effervescence The other word for effervescence that is accepted is bubbling or fizzing. The inference for that, hydrogen ions or hydroxonium ions or RCOOH present. And having given that observation, it means whenever you are adding sodium carbonate or sodium hydrogen carbonate, you expect to only see that or no effervescence. So you either see effervescence or you see no effervescence. Do not say sodium carbonate dissolves and remains in solution, or it settles at the bottom. That will not be marked. What is marked is simply, is there effervescence or no effervescence? So the negative of that would be no effervescence, no effervescence, or no bubbles, or no fizzing, and the inference would be those three groups are absent. Those three groups are absent. There are words that are rejected. Hissing is rejected by the exam council, though it is in some books. The exam council argues that hissing is a sound produced by snakes and has no relation to the sound produced in the chemistry lab. We reject fizzling. Fizzling, and we reject sizzling. To fizzle is to die off slowly. Like a fire that was burning and it is going off, we say it is fizzling. To sizzle is a type of a dance. So those are not chemistry terms. When you use them, you fail. And one thing that we must know about all qualitative analysis, if you do not score the full marks at observations, full marks, the inference is not marked. We simply put an inverted V. If the observation was supposed to score 2 marks and you score 1 mark or 1.5, we do not mark the inference, whether it is correct or wrong. So for the inference to score, the observation must score fully. Number 6, addition of magnesium ribbon. Addition of magnesium ribbon. The observations and the inferences are similar to those of sodium carbonate or sodium hydrogen carbonate. However, the 2 times that magnesium ribbon has been used, candidates are supposed to go a step ahead and describe the test of the gas produced. So for magnesium ribbon, effervescence or bubbling or fizzing, but you go a step ahead to mention producing a gas which puts off a burning splint with a pop sound. You must go a step ahead to describe the test for the gas produced. And at that point also, important to note that hydrogen gas does not burn with a pop sound. If you say a gas that burns with a pop sound, again, you fail on the mark. It's a common mistake in textbooks. Hydrogen burns quietly. It does not burn with a pop sound. It puts off a burning splint with a pop sound. Puts off a burning splint with a pop sound. So the inferences are the same. Hydrogen ions, hydroxonium ions or RCOOH present. Every test also has its negative. So the negative of that test would be, again, no effervescence or no bubbles, no fizzing. Test number 7. Addition of potassium manganate 7. Addition of acidified potassium manganate 7. Addition of acidified potassium manganate 7. Expected observation, and here it's very important, you must mention the two colors, first color and the final color. So you must mention purple potassium manganate 7 changes to colorless, or the color of acidified potassium manganate 7 changes from purple to colorless. You must mention the two colors. Secondly, it is the potassium manganate 7 that is changing color and not the solution. So don't say solution changes from purple to colorless, because it would be a contradiction. At the first step, you could have mentioned solid dissolves to form a colorless solution. Then later on, you start saying solution has changed from purple. When did it change to purple? And you said the solution was colorless. So it's the potassium manganate 7 that changes from purple to colorless, not the solution. Inference or inference, carbon to carbon double bond or carbon to carbon triple bond or ROH present. The negative of that test is purple potassium manganate 7 remains purple. Potassium manganate 7 retains its purple color. And the inference would be those three are absent. You can also say purple potassium manganate 7 does not change to colorless. We also accept purple potassium manganate 7 is decolorized. Purple potassium manganate 7 is decolorized. However, we reject the word discolored. So get the difference. We accept decolorized, but we reject discolored. Decolorized means it changes to colorless. Discolored means it faded and maybe got another color. So it's important we know that when we are using potassium manganate 7, we are only expecting it to change from purple to colorless. There are no intermediate colors. When you are using potassium manganate 7 and it gives another color, notify the teacher or the lab technician to have it acidified and repeat the test. Because we reject those colors. It can form a brown color. It can even form a black color if it was not well acidified, because instead of forming manganese 2 ions, it could form other oxides of manganese, which are brown, manganese 3 oxide, or which are black, manganese 4 oxide. So in case it gives any other color, never record that color or that observation. Simply know it was not well acidified, and probably inform your teacher or lab technician so that you can be given one which gives those results. Test number 8, addition of potassium dichromate 6. Of course, which is acidified. Acidified. Observations and inference. Color of potassium dichromate 6 changes from orange to green. The inference is simply here ROH present. The negative of that test is color of acidified potassium dichromate 6 remains orange. Remains orange. Where you say ROH absent. Now these tests for qualitative analysis, the tips that I'm giving to you simply implies whenever you come across this test, there are only 2 possible observations. You cannot record anything else. You either record the first observation or the negative. You cannot have any other in between observations. And the inference is, as I've mentioned. Test number 9, addition of bromine water. Addition of bromine water. Observations and inference. One clarification and a mistake in textbooks, which the exam council rejects: bromine water is never brown nor red. So those colors are rejected. It is either orange or yellow. Those are mistakes even in textbooks. So it is either orange or yellow. So the observation is that orange or yellow bromine water changes to colorless. Orange or yellow bromine water changes to colorless. or is decolorized. The inference would be the unsaturation or unsaturated functional groups, carbon to carbon double bond or carbon to carbon triple bond present. The negative of that would be orange or yellow bromine water retains its color. Orange or yellow bromine water retains its color. When you are recording, of course, in an exam, don't use the word or. You use the color that you have seen. Should either see it being as being orange or being yellow. Those are the acceptable colors. Don't record both. And the last test, test number 10, which is our final. Addition of ethanol plus sulfuric 6 acid, then warm. Addition of ethanol plus sulfuric 6 acid, then warming. Expected observations. This is the only test where we do not observe with our eyes, but we smell with our noses. So you observe with the nose. Observation, pleasant smelling substance formed. Pleasant smelling substance formed. We also accept fruity smelling substance formed. We reject, very common also in the textbooks, we reject sweet smelling substance. Sweet smelling substance. Quite a number of textbooks have that mistake. And simple, the exam council insists that sweet is not a smell, it is a taste. So you can't say a substance is sweet smelling. You can only say it is sweet tasting. The inference here is RCOOH present. RCOOH present. Do not say ester present, because ester was not in the original substance. It has just been formed for the pleasant smell. So it is not in what you are testing. It is a product that has been formed. So if you write ester present, it does not score. Also for the same test number 10, a converse test can be performed. So conversely also, addition of ethanoic acid plus sulfuric 6 acid plus warming. So you can have conversely addition of ethanoic acid plus sulfuric 6 acid plus warming. The observations the same, but the inference here would be now ROH and not RCOOH. That is, if you could add ethanoic acid plus sulfuric 6 acid plus warming, fruity or pleasant smelling substance, and the inference now would be ROH present. Now that test number 10 brings us to the end of the chemistry paper 3 talk. And at that point, just to mention that this is a paper that we have seen over the years, candidates scoring very high marks, as high as 39/40, year in, year out. Also important for you to know, why is it so easy to pass in this paper? The exam council does not allow us to award even zeros. So we try to look for marks for you. We have marked previously and seen very interesting answers where we are still told to award answers that have even spelling mistakes, mother tongue interference, like the part of effervescence. We have seen that and we have awarded fully. We have seen this. We have seen that and awarded fully, and many others. So one thing I want to emphasize to all of you candidates or students listening and the audience, this is a paper that is student friendly. It is the only practical paper where the teacher influences the results or influences the marking for the students. It's the only practical paper where the teacher performs the practical and gives the results. It's the only paper where all candidates' answers are marked correct. You use your results for the calculations and you score fully. So whenever you face the exam, face it with confidence. Do your own work, because your own work could earn you your good grade. If you can manage at least 16/40, then you can be safe from a D grade in chemistry. So you can imagine when you see so many D's and E's in chemistry, what the candidates scored in the practical. And as you have seen, the marks are easy to score. Marks are easy to score. Analysis of the exam over the last 5 years shows that if a candidate who is in quotes obedient or keen, who follows the procedure, simply fills the table, assuming the candidate is a Form 1 student, follows the procedure, does the experiment, fills in tables, does the qualitative analysis, and simply records the observations. This candidate who does not know chemistry, but has just followed instructions as an obedient student, the minimum marks that that candidate should score has always been above 20 in the last 6 years. 21 marks, 23 marks, 20 marks for just tables, that is filling of tables, drawing of graphs, and recording observations only without inference, because inference is now the knowledge of chemistry. But observation is simply your ability to follow instructions. You can easily score 20 and move out of the D grades if you are just keen with the practical. At this point, I want to wish you all and the audience who are watching from elsewhere all the best and welcome for feedback or questions. Okay, let me respond to the questions. I'm seeing those who asked are still online. The first question was from Ketulu Day. How do you distinguish between carbonate and sulfite ions. So carbonate ions and sulfite ions, I did mention they are distinguished by addition of or let me begin this way. Supposing they are insoluble solids or in solid form. Supposing they are in solid form, addition of an acid would cause both of them to produce effervescence. Addition of an acid would cause both of them to produce effervescence. Now the gases produced for carbon 4 oxide, if the gases produced are tested using potassium dichromate 6 paper or a paper soaked in potassium dichromate 6, for carbon 4 oxide, the paper would remain orange, but for carbonate, the paper would remain orange, but for sulfite, the paper would change from orange to green. Or in short, both of them react with an acid to form salt, water, and a gas. Carbonates react to form salt, water, and carbon 4 oxide or CO2. Sulfites react to form salt, water, and SO2. You can now distinguish the two gases by testing using potassium dichromate 6 or potassium manganate 7, where sulfur 4 oxide changes dichromate 6 from orange to green, or manganate 7 from purple to colorless. There was a question from Machakos Baptist. Second question, how do you distinguish between an organic and an inorganic test? How do you distinguish between an organic and an inorganic test? Now, normally, or the tradition has been, the organic test comes last, is normally the last question. And secondly, organic tests, normally the first tests are tests involving burning or combustion, ignition. So immediately you do that, you know this is an organic test that you are performing. Thirdly, in the previous past papers, the organic qualitative analysis question starts with an opening remark. You are provided with an organic solid P. So that way, from the question, you know it is an organic qualitative analysis test. Question from Kcse: whether when a wooden splint has been heated, has it been burnt or lit? I think an English teacher would answer that best. Burnt means it has already been consumed by the fire. In my own understanding, lit is when it is showing light or burning. So I think that is just a matter of English, but in chemistry, we will not so much be keen on that. Kitulu Day, the teacher asked, how can one distinguish lead-2 ions and aluminium ions? How can one distinguish lead-2 ions and aluminium ions? I will give 4 eliminative tests for the same. Test number 1, supposing you had lead-2 and aluminium that you are suspecting. Test number 1, addition of sodium hydroxide dropwise till excess. The observation would be white precipitate that dissolves in excess. Of course, at that point, we would infer ZAP, zinc, aluminium, lead 2. The subsequent test would be addition of ammonia solution. The observation would be white precipitate insoluble in excess, where now the zinc is eliminated. We are left with now lead and aluminium, lead 2 and aluminium. Now, distinguishing at that point, there are two possible tests. First one could be addition of sodium sulfate or addition of sulfuric 6 acid or addition of sodium chloride. Now take note of those three substances, or a chloride and a sulfate. Either of the two would distinguish lead 2 from aluminium by the fact that lead 2 forms precipitates with any chloride or any sulfate. That is one of the tests that would distinguish basing on the precipitation reactions of lead 2 salts or lead 2 cation. The other one would be now basing on the fact that aluminium carbonate does not exist and is hydrolyzed by water to give effervescence. So the other test would be now addition of sodium carbonate solution. Addition of sodium carbonate solution. So if it is lead 2 ions, then it would simply give white precipitate. But if there are aluminium ions, there would be effervescence at sodium carbonate. Remember, this is a subsequent test after having performed the two tests with the sodium hydroxide and with ammonia solution. This is a third test. So we say the third test can be either a sulfate or a chloride or a carbonate. And for the carbonate, we have said if it is lead 2 ions, it will simply be a white precipitate. If it is aluminium ions, there will be effervescence. Effervescence and then a white precipitate. Effervescence and then a white precipitate. That is on the fact that aluminium carbonate, upon being formed, is readily hydrolyzed. And after being readily hydrolyzed, it forms aluminium hydroxide, which is a precipitate. There is a question number 5 from the host, David Kioko. What are the possible observations and inferences for addition of potassium iodide? Potassium iodide has been used or can be used twice in 2 different tests. The first one is where we mentioned in 2006, can be used as a reducing agent, where it reduces ion 3 to ion 2. The second test, potassium iodide, is used to confirm the presence of lead 2 ions. Confirm presence of lead 2 ions, where a yellow precipitate is formed. There was another question, number 6, for Chama, host from Chama. The inferences for addition of observations for addition of acidified potassium manganate 7 or acidified potassium dichromate 6, whether we can say the color persists. Very correct. But insist on the color. That is the negative tests for potassium dichromate 6 or potassium manganate 7. You can mention orange color persists. purple color persists. Those are acceptable. Question number 7 was from Amos, the grading system in chemistry. Grading system in chemistry has always been the top secret of the NEC CEO. The NEC CEO and the chief examiners, that is their top secret. However, just a hint and not to give you false hope, go for the Kenya National Exam Council report. Every year they give a report. Like there is a current one on Kcse 2019. Go look at the average mark for chemistry every year. Of course, I think last year it was 26.2% in the entire republic. Now they decide, normally, this is from a source, that average mark normally has always been pegged at D+. D+ as the median, D+. So from there, if the average is maybe 27, 29, 32, place the D+ there, and now spread the other grades appropriately. There was a question, number 8, by Ian, on the letters for symbols of elements. We are very strict on the symbols of elements. That is in Form 1 chemistry. And we even advise Form 1s, if you have a challenge, revisit very important notes. That is grade 2 and grade 1, or standard 1 and 2 notes, where they were being taught handwriting. Letters of the alphabet. Because if that time you did not take that teacher seriously, now is when you will reap the bad fruits of that time. If you did not take your standard 1 and 2 teacher seriously in chemistry, letters of the alphabet are very key, especially when we are writing symbols. Magnesium, M must be uppercase, G must be lowercase, in terms of the size and in terms of the appearance. The M must be one where there are straight line segments joining, not curves. And the G must be one where it has a descender or going below the line, and many others, such that touching letters, when you write touching letters, calcium, C and A are touching, the exam council says that is not a letter of the Roman alphabet that we use. C and A, they say you have invented your own letter, probably in Arabic or Russian. It is not a normal letter. So the letters should not touch and should be printed block as required. Question number 9 was from Brian here, that I mentioned on quantitative analysis, and I gave all the areas, are all the areas tested, not unless the practical is to take a whole day. For 2 hours, the part that is tested is normally a titration combined with enthalpy, one of the enthalpies, a titration only, an enthalpy only, or 2 enthalpies, rate of reaction only, cooling curve only, etc. So it is, we have never had more than 2 areas out of the 5 areas I gave being tested. That would take a very long time. I think I've answered all the questions.
Okay.